many tons of ore to get just a few grams of gold. It's very costly to extract in large amounts. And this makes it so that the supply doesn't increase very rapidly, and even if the demand were to increase a lot, it's still very, very hard to increase the demand. You can't just, it's not like the bottle factory where you can just create 1 million more bottles if you want. There's a certain limit to how much gold you can extract from the earth profitably. There's a lot of gold in the oceans. It's estimated that there's probably tens of millions of tons of gold in the ocean. Unfortunately, we do not, or fortunately for better or worse, we do not have right now a technology to be able to extract it economically. It's still much more economical to get it from dirt. And there's also asteroid mining, which is something that might be possible in the future, but right now it's still not the cheapest way to get gold. So these are other sources of gold that could potentially disrupt the market if the technologies were to be developed to make this actually more economical than digging in the ground. And it must be expensive to alter. And now this is something that I talked a little bit about before with the shaving of coins, where you can actually melt down a gold coin and mint it into something else, but there's a certain cost associated with that. So, and there's a certain cost associated with making all the stamps and everything to be able to actually make the coins. So it means that people that get those coins probably are not going to want to alter them too much. But this actually applies much more to cryptocurrencies because this is fundamental. This is not something that you can just kind of rely on the physical property of something. It's something that needs to be designed into the system and artificially imposed. And it must be expensive to duplicate, which I'll get into in a second. I'll go over these one by one. So in trying to recreate scarcity in digital technology, in order to have the verifiability, we use cryptographic hash functions. And then we use public key cryptography for the stuff that needs signatures to authorize. But for all the stuff that is basically permissionless, everything is done with hash functions. Now, a hash function, as you're all probably familiar with, takes something like this wonderful picture of a cat, right? Any file, any data, any digital data, and sticks it into a meat grinder, right? and spits out a fixed length number. You stick a different picture in there, you're going to get a different number. You stick the same picture in there, you're always going to get the same number. And of course, for it to be really useful as a cryptographic hash function, it must be difficult to be able to find some picture, without knowing that this picture generates this, to find another picture, basically a pre-image that would compute this. And given this number or this, this output, it must be very, very, very difficult to figure out that it was produced by this cat. In fact, here it would be impossible. And this allows you to know that anyone that gives you this number probably processed that picture, to that picture at some point. They computed it. There's no intrinsic scarcity in that. You can always build better technology. I mean, there's the speed of light and other kinds of limitations in physics. But other than that, basically, digital data is not expensive to produce. And so Adam Back invented a hash cache, which was a really clever idea with where you take an email and you add an extra field where it has this extra random string nonce, basically, that this is the key insight. When you take the hash of the whole thing, even though you can't actually do a pre-image, you can do a partial pre-image. Basically, you can do a partial hash where you say only the first few bits need to be 0, not the whole thing, right? And so this allows you to give a certain difficulty in terms of the percentage of numbers of different possible pictures that would actually give you a hash that gives you 0. Basically, the first few bits of the string, its output is 0. So in this case, you have the same cat picture, and you add a nonce to it. You stick it in the meat grinder again, and you get this output. And now we have got this leading zeros, right? So this requires work. So this leads to the concept of proof of work, right? So this makes it costly to produce this. So now you have this cat picture with that nonce. That combination now is scarce. But that's not enough. Now you need to also know that the supply of the coins are going to be scarce. There's not going to be too many coins existing. So you need to define a rule that determines how many actual objects are in existence. And so this gives us the halving intervals and everything. That basically, there's a 21 billion limit that exists. And this makes it so that, and there's also a distribution in how this currency is distributed. The more that the hash power is distributed geographically and politically, if all the gold mines were in one particular country, that would give that country very, very major strategic advantages. Just get some water. So now, to be expensive to alter, Satoshi Nakamoto came up with this idea of a timestamp server. And actually, this idea in itself predates Bitcoin by quite a bit. The idea of chaining blocks and having one commit to the hash of the previous one, right? Now, this in and of itself does not tell you that the first block happened before the second one, but it does tell you that the first one was computed before the second one. You can still change the order of things, right, and recompute it, but at least you know that this block, without computing the first block in the sequence, you cannot compute the second block. So a good example of this is Git, which is the open source tool developed by Linus Torvalds that's used ubiquitously in cryptocurrency development and practically everything else, which uses this concept, even before Bitcoin, of chaining a set of commitments, and that allows you to have a history that allows you to know that every single commit in this sequence it had to be computed before the next one. It doesn't mean that it happened in that order, that code was written in that order, but it does mean that they had to be computed in that manner to produce these hashes. So the problem was, how do you now make it so that it's very hard to actually change the order of these things, right? You need to make that expensive as well. So that's where, in the case of a Git workflow, for instance, you don't necessarily just have one chain, right? You have this directed acyclic graph, essentially, a whole bunch of different potential trajectories, and you get merges, and you can get rebases, which is what it's called when you change the history of stuff, where you don't necessarily have one master branch that everyone is going to agree on. You can clone a repository, and you can create a separate master branch that you want, and there's not necessarily going to be an agreement on which is the official master branch for everyone, right? Which is not a problem in most open source projects, because there tends to be a maintainer that people think does a good job, and if they don't like him, they'll sack him. Right? So for open source development, this is generally not a problem, and actually you want to be able to change stuff because you don't want to be stuck with some buggy code that you wrote and now you can't fix it, you can't refactor anything anymore, and everything has to stay there for all eternity, right? But that's not something you want with something like with a cryptocurrency, with money. So so Satoshi Nakamoto came up with this idea of cumulative proof of work, which I think is probably the key invention, or the key idea in Bitcoin, right? You have many potential branches that can come off, but the most difficult chain is the one that everyone tends to converge upon. And the fact that it's the most difficult one means that it is the most costly one to create, which de facto makes it the most scarce, which is the one that everyone wants. And this works as long as all the blocks are evaluated using the same rules. Every single block must be checked using the exact same consensus rules. If blocks are checked using different rules, then all bets are off. Depending on the kinds of rule changes that you make, there's no guarantee that you're going to get a convergence. And that's what you get when you get chain splits, right? So what about proof of stake? So in proof of stake, rather than relying on the costliness of proof of work, what you do is you have coin holders vote whenever there's a split on which one they want to follow, right? And this is an example from Casper, which is a proposal for Ethereum right now, where basically the idea is that 2/3 of the coin holders need to vote on a particular chain for it to become official, and as soon as that happens, the other coin is invalidated. Now, there's a problem with proof of stake if you're just doing this naively, which is that the cost of computing hashes is real. You need to expend energy to do that. But the cost of voting in principle is nothing. So what proof of stake schemes have tended to do now is to try to have some kind of slashing where you can only vote on one chain, and if you vote on more than one branch, all your coins are taken, or you get severely penalized for it. And this does seem to be convergent. It seems that eventually everyone will there might be several succinct way.